Okay, here we are in the third and final video for the angular kinematics topic. So in this last lecture video, we're going to focus on the relationship between linear and angular kinematics. So we're going to learn about the relationship between angular and linear displacement, between angular and linear velocity, and between angular and linear acceleration. Okay, hopefully none of this is a surprise to you at this point. I think this is the third time that I mention the different types of motion, but on this slide, I'm just summarizing at this point those three different types of motion, and I've highlighted in this sort of pinkish red color what the important distinction is for each type of motion. So in a rectilinear motion, the motion occurs along a straight line. In a curvilinear motion, then the motion occurs along a curved path, and an angular motion occurs about an axis of rotation. Okay, so the first step in relating angular and linear motion is noticing that for each linear motion quantity, there is an angular analog. And we previously learned about all these linear motion quantities in week 5, and now I'm presenting you with the angular motion analogs in week 6. So if we think of displacement, for example, this first row here, in a linear motion, displacement is represented just by x, right? Displacement in the x direction would just be x, whereas in angular motion, displacement is represented by theta. Initial and final velocities are represented by VI and VF for linear motion, and by omega I and omega F for angular motion. And then so on and so forth. So for every linear motion, there's an angular analog. So now the same equations of constant velocity and constant acceleration exist for both linear and angular motion, but you just substitute the linear quantity with the angular quantity. And I won't walk you through each of these equations because you aren't expected to memorize them, but I just wanted to illustrate for you that the equations are virtually the same for linear and for angular motion. You're just substituting those different variables that I just showed you on the previous slide. Okay, let's dive into specifically relating linear and angular displacement now. And let's do that with a little virtual experiment together. So I invite you to put one arm out on the table in front of you. And now flex at the elbow and bring your hand towards your shoulder as far as it can go while keeping your elbow still. All the parts of your forearm underwent the same angular displacement when you did that. But which part moved further? Your hand or the point of attachment of your biceps muscle that's close to your elbow? Which one moved further? I would say it's your hand. This figure here represents that experiment that we just did. So point A over here is your hand, and point B is the attachment of your biceps muscle. So the linear distance of the arm is represented by LA over here, and the linear displacement of the biceps is LB over here. And the linear distance is the same thing as the arc length of the movement. Okay, and then the linear displacement that the hand traveled is dA. So this was the linear distance over here, arc length, and then this is the linear displacement that the hand traveled. So these two values, LA and dA, are both larger than LB and dB. So basically, how far any point on the arm moves when you flex your arm is dependent on how far that point is from the elbow or from the axis of rotation. So let's look at the definition of an angle measured in radians because it'll make this relationship more obvious. So an angle measured in radians is the ratio between the arc length and the radius. And that's exactly what is shown here in the angular displacement equation. So if we manipulate that equation, then linear distance, which is arc length, that linear distance that's traveled by a point on a rotating object is directly proportional, so it's equal to the angular displacement of that object and the radius, or the distance that that point is from the axis of rotation. So if the angular displacement is measured in radians, then the linear distance traveled, or the arc length, is equal to the product of the angular displacement and the radius. Now, this is only true if this angular displacement is measured in radians. That's the only way this relationship works, is if this angular displacement is in radians. So I'll repeat all of that in a condensed way here. So the curvilinear motion of a point on an object can be related to the angular motion of that object using this formula here. So L is equal to delta theta times R, which means arc length is equal to angular displacement times the radius. Now, there are two things that are super important to remember for this relationship to be true. First, like I said, the angular displacement must be in radians. And then second, the units of length for arc length and for the radius must be the same. So both the arc length and the radius have to be in millimeters, for example, or in meters. They just have to be the same. So thinking of this relationship between angular displacement and linear distance or arc length, why do you think track races use a staggered starting position? And I invite you to pause the video here and actually think about it and write out an answer for this as if you were writing a question or an answer to a question on a test. So this is a staggered start here. And the question is, why do they do that in races? Well, the track is curved, right? So picture the axis of rotation as being in the very center of the track field. And without a staggered start, runners in these outside lanes over here would run a farther distance because the radius of the curve that they have to run would be larger than the radius of the inside runners over here. Right? So the larger radius causes the length of their lane all around. So the arc length that they would have to run would be longer. So that's why the staggered starts exist. Okay, let's apply what we just learned to a hockey stick. So all points on the stick undergo the same angular displacement, which means also the same average angular velocity because they all take the same time to undergo that angular displacement. But a point on the stick closer to the blade, so further from the axis of rotation at the top of the stick, this point moves through a longer arc length than a point that's closer to the axis of rotation, right? That's what we just learned. And here's the equation to remind us. So arc length is equal to angular displacement times the radius. So the 2 points travel their respective arc lengths in the same time. The point further from the axis of rotation must have a faster linear speed because it moves a longer distance, but in the same time. And mathematically, this relationship can be derived from the relationship between angular displacement and linear distance traveled. So this relationship here, this equation. So if we divide both sides by the time that it takes to rotate through the displacement, then we have this equation here. Now, look at the term on the left side of the equation. Distance over time. That's speed. And then on the right, angular displacement over time is angular velocity. So let's simplify those terms, and we end up with this equation. So average linear speed, denoted by S over here, is equal to angular velocity times the radius. So there's this relationship between linear and angular velocity as well. Okay, time to test our knowledge. So here's a practice problem. During Charlie's golf drive, the angular velocity of his club is 0 at the top of the backswing and 20 radians per second at the bottom of the downswing just before hitting the ball. The downswing lasts 0.2 seconds, and the distance from the club head to the axis of rotation is 2 meters at the bottom of the downswing. What is the linear speed of the club head just before hitting the ball? So I encourage you to pause here and try to work through this calculation on your own. Okay, so always starting with what we know. We know the initial angular velocity is 0 radians per second at the top of the backswing, right? Not moving yet. And the final angular velocity is 20 radians per second at the bottom of the downswing just before hitting the ball. We also know the time it takes for the downswing, which is 0.2 seconds. And we know that the radius is 2 meters. And we're looking for the linear speed of the club just before it hits the ball. So in this case, we actually have more information than we need here. We don't really need the initial angular velocity and we don't need the time because we just want to know the linear speed at a specific time, right? Just before hitting the ball. So let's just use the relationship between linear speed and angular velocity. So we see that the speed is equal to 20 radians per second, right? That final angular velocity times the radius, which is 2 meters. And remember that angular velocity needs to be in radians. Otherwise, the units don't work out in the end. So in this case, we're fine. We don't need to convert. So do you notice here how we ended up with 40 meters per second as our speed? That's because this was radians. If we had the angular velocity in degrees, then we would have some weird thing like 40 degree meters per second. And that should be a hint that that didn't work out properly. So remember, always have your units for angular velocity in radians per second so that this relationship works out fine. And your linear speed makes sense, right? 40 meters per second, that's a reasonable unit for speed. So to answer the question, the linear speed of the club head just before hitting the ball is 40 meters per second. Okay, last topic to cover in this lecture is the relationship between angular and linear acceleration. So here it's important to remember the relationship between linear and angular velocity, what we just saw, where the angular velocity of a spinning object increases, then the linear velocity of a point on the object will increase as well, right? Because they're proportional to each other. So this means that naturally, the angular and the linear accelerations of a point on a spinning object are also related. And the easiest way to understand linear accelerations that are caused by rotating objects is to resolve that acceleration into its perpendicular components. So if we have an angular acceleration in this direction, the easiest way to see that relationship is to break that acceleration down into its two perpendicular linear components. So in this case, we have the transverse component, AT, this way here, and we have the radial component, AR. And think of radial as the radius, right? So the radial acceleration is along the radius. So the acceleration in the transverse direction is known as tangential acceleration, and the acceleration in the radial direction is known as centripetal acceleration. They're both linear accelerations that are caused by angular motions. So this means that they're similar concepts, they're just in different directions. So let's just take a closer look at each of those different components now. So let's first talk about tangential acceleration. It's called tangential acceleration for a reason. Remember that a line is tangent to a circle if the line intersects the circle at just one point. So in this case, this line here only intersects this circle at this specific point here. The component of linear acceleration that's tangent to the circular path of a point on a rotating object is called the tangential acceleration of that point. So tangential acceleration is related to the angular acceleration of an object like this. A point on a rotating object undergoes a linear acceleration that's tangent to its rotational path and equal to the angular acceleration of the object times the radius. And that's this equation here. So tangential acceleration is equal to angular acceleration times the radius. Okay, the other linear acceleration that's caused by angular motion is called radial acceleration. And radial acceleration is a linear acceleration that's directed towards the axis of rotation, towards this middle part here. And for this reason, it's often also known as centripetal acceleration because centripetal means center seeking. Radial acceleration represents a change in direction of the angular motion. So there needs to be this linear acceleration towards the middle, otherwise it would just travel tangentially. And hopefully I can clarify this with an example. If you were to tie a weight to the end of a string and make it spin in a circle at a constant angular velocity, which way would you need to pull on that string to keep it moving in a circle? You would have to pull on the string with a force that's directed towards the center of the circle, towards the axis of rotation. And that's because of this centripetal acceleration. There are two formulas to define radial or centripetal acceleration. The first uses angular velocity. So here, the radial acceleration is the square of the angular velocity times the radius. The second equation uses tangential or linear velocity. So in this case, radial acceleration is the ratio between the square of the tangential velocity and the radius. So let's just end with a calculation to make sure that we understand. So a hammer thrower spins with an angular velocity of 1200 degrees per second. The distance from his axis of rotation to the hammerhead is 1 meter per second. What is the centripetal acceleration of the hammerhead? So again, please pause the video now and try to solve this one yourself. Okay, so we know that the angular velocity is 1200 degrees per second and that the radius is 1.2 meters. And we're looking for the centripetal acceleration. So it looks like we have everything we need to plug into this equation here. Except for one thing, our angular velocity is in degrees per second. And we absolutely need that to be in radians per second for this relationship over here to be true. So let's convert that before doing anything else. So remember the magic number. There are 57.3 degrees in 1 radian. So we cross multiply 1200 degrees, divide by 57.3 degrees, and we end up with 20.9 radians, rounded up to the first decimal here. Okay, so now we're ready to plug everything into our equation. So radial acceleration is equal to the square of angular velocity times the radius. Plug in our numbers here, and we end up with a radial acceleration of 524 meters per second squared. So to answer the question, centripetal acceleration or radial acceleration of the hammerhead is 524 meters per second squared towards the axis of rotation. We made it to the end of the week 6 content. So in this last video, we really put everything together that we've learned over the last 2 topics, learning about the relationship between linear and angular kinematics, specifically about the relationship between angular and linear displacement, angular and linear velocity, and angular and linear acceleration. Now, as I hope you know, the midterm is taking place next week on OnCue. So I will not be posting any new lecture content next week. There is, however, still tutorial for those groups that haven't done the linear kinematics tutorial yet. Okay, best of luck with the midterm, and don't be afraid to post your questions in the discussion board on OnCue if there's anything that you're not sure of.